Welcome everybody to my presentation of a closed form analysis of crack initiation in layer system under thermal loading. My name is Debora Linn. I'm from Technical University of Darmstadt. My supervisor is Professor Becker. So let me start with the agenda. After a short introduction and presenting of the topic, I would like to directly continue with the modeling. This means the development of an analytical model on the basis of three different load cases. A stress analysis is carried out where the analytical model is compared and validated to a numerical model. Then follows a failure prediction within the framework of finite fracture mechanics, and then a short conclusion. So the topic of my talk is the development of closed form analytical approach for a simple generic configuration. This generic configuration serves as a simplifying model for many different applications or situations. For example, if you have a look at concrete structures that are locally reinforced or repaired with reinforcing patches, the debonding of these reinforcing patches is very important to analyze. Another example where the initiation of debonding cracks is very important, or a typical failure case are, like you've seen it before, the single lap joint or a double cantilever beam. So let me continue with the situation we have a look at. So we look at the situation of a patch on a substrate under thermal loading, like you see it on the right. Both layers are modeled with linear elastic material behavior. And now the idea is to reduce this situation to the overlap length to get a generic configuration. The advantages of this generic configuration is that other load cases can be applied as well. You only have to apply other boundary conditions at the edges on the left and right. So goal is now to get an approximate closed form analytical description of the deformation stress and strain field within these layers. So for the displacement, I choose a closed form analytical description of the displacement. I choose a higher order displacement approach, like you see it here. More precisely, it's a second order displacement approach, which is extended with an additional term. If you have a look at the situation in head, you see that stress singularities appear at the edge between both layers. And these stress singularities are taken into account in this additional term. So that's the reason why here's standing this 0.7. That's the singularity order of the system. So yeah. So goal is now to determine these unknown functions dependent on x, which is done with the principle of minimum total energy. This says that the total potential must become minimal. Potential energy consists of the internal potential and the external potential. As we have no external loadings acting in our configuration because we only consider thermal loadings, the external potential is equal 0, and the total energy only consists of the internal potential, which is determined which is calculated from the strain energy, like you see it here. The first integral describes the strain energy of the first layer, and the second integral the strain energy of the second layer. So in the next step, Hooke's law, kinematic relations, and the displacement approach are inserted into the total energy, so that the total energy only is dependent on functions dependent on x. So returning to the minimum total energy principle, it says that the extremum of the total energy must become 0. So applying the variation of the total energy to the variation of all displacement variables leads to the equation you see here. The brackets you see with the dots are placeholders and describe in sum a non-homogeneous differential equation system. and the corresponding boundary conditions. This differential equation system is a system of second order and must be reduced to a first order system to get a solution. As I said before, the differential equation is non-homogeneous, so the general solution consists of an homogeneous and a particular solution. While the particular solution is determined by using the method of undetermined coefficients, the homogeneous solution is generated by solving an eigenvalue problem. So we have this general solution like you see it here. Here the constants C1 to C28 must be determined, which is done by evaluating the 28 boundary conditions. So evaluating these boundary conditions leads to the deformation field, and based on the deformation field, the strain and stress field within the layers are known. So the stress analysis can be carried out. As I said before, the analytical model is now compared and validated to a numerical model within the stress analysis. So for the numerical model is modeled by finite element method in the program Abacus. You see it here. It is discretized in a way that the mesh is at its finest at the free edge between both layers at the interface, and it's getting larger towards the other edges. The model has about 1.1 million degrees of freedom. There are quadratic basis functions used, and it requires something about 70 seconds to calculate. So now let's have a look at the stresses at the interface between both layers. You see them here for the situation of a patch on a substrate under thermal loading. The stresses, the interlaminar stresses at the interface, you see on the right-hand side. The curve in blue represents the field stress, sigma z, and the curves in red describe the interlaminar shear stresses. The solid lines are the results from the FEM, and the dashed lines are the results from the new analytical approach. So compare both curves separately to each other shows that there are very good agreements between the new approach and the FEM. Also, the stress angularities at the free edge are approximated very good. So as I said before, this generic configuration can serve as a simplifying model for other load cases as well. For example, for the double cantilever beam, you see on the right, on the left, and the single lap joint you see on the right. And again, the stresses are shown at the interface between both layers. And again, there are very good agreements between the new approach from the analytical model and the FEM. So we can go to the failure analysis within the framework of finite fracture mechanics. So to model a crack with the analytical model, the model must be extended. So we mentally divide this model into two areas. The first area is the purple one, that's the cracked area, and the second area, it's the uncracked area, which is modeled as before. So when calculating the displacements in this model, you have to choose different displacement approaches for the left one and for the right one. And when solving an eigenvalue problem, you don't only need the boundary condition on the left and on the right, you also need transition conditions at the transition between both areas. The rest of the procedure remains the same, so the failure prediction within the framework of finite fracture mechanics can be done. So finite fracture mechanics, I use a coupled stress and energy criterion, which was postulated by Linn. And it says that a crack of finite length will instantly form when coupled stress and energy criterion are fulfilled simultaneously. As a stress criterion, we use a quadratic stress criterion, which considers the interlaminar stresses at the interface between both layers for the uncracked model. So that are the stresses I shown already. And for the energy criterion, we use a linear criterion, which considers the incremental energy release rate, which is calculated like you see it here. So here are the interlaminar stresses and the crack displacements. So let's have a look at the crack opening behavior and the incremental energy release rate, which is resulting from it. So on the left, you see the crack opening displacement. In red, it's delta U, so it's the data displacement in length direction. And in blue, you see the crack opening in thickness direction. Again, there are good agreements between FEM and the neural approach. And on the right, you see the incremental energy release rate in blue for mode 1, in red for mode 2, and in black, the sum of both. So again, there are very good agreements, so that the coupled stress and energy criterion can be evaluated. This is shown here. So the curve in orange shows the stress criterion, and in green, it shows the energy criterion. So again, going back to the coupled criterion, both criterions must be fulfilled, and this is the case when both criterion are greater or equal 1. So for a temperature load of minus 189 Kelvin, the stress and energy criterion are simultaneously fulfilled for a crack length of 2 millimeters. Yeah, also you can see that the energy criterion is decisive for failure. So for example, if you apply a higher load, for example, minus 10 degrees, the energy criterion will be here, so there are no failure. So let me close the presentation with the short conclusion. So I considered a very simple model of a two-layered system, which serves as a simplifying model for different load cases, for example, a patch on a substrate under thermal loading, or adhesive joints like a double cantilever beam or a single lap joint. I developed an approximate closed form analytical approach to describe the deformation, strain, and stress field within these layered systems. I carried out a failure analysis within the framework of finite fractal mechanics, where I used the coupled stress and energy criterion to predict the initiation of a crack. And it shows that the results between the new approach and the FEM are very good. And other advantages of this analytical model are that it gives a more physical insight and allows parameter studies very good. And the much shorter calculation time is a further point to say. So thank you very much.